Welcome to the Petro Papers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm Yogashree Pradhan, and with me here today, I have the USI team. I have Duke Lamb, who is the co-founder and the CEO of TechUSI. I have Kyle Hanna, who is a senior reservoir engineer. And I have Tui Nguyen, who is a founder of the AI platform and one of the reservoir engineers for TechUSI. Today, we're going to talk about URTEC 3723394. Paper title and the description is in the description box below for viewers and listeners on YouTube and Apple Podcasts. I'm going to read a little bit about each one of them before we start peppering them with questions. Duke Lamb is the founder and CEO of Unconventional Subsurface Integration LLC, or TechUSI. He also worked as a senior reservoir engineer at the Global New Business Development Permian Basin at Hess Corporation and a senior reservoir engineer for new ventures in China, Canada, and Williston Basin for Hess Corporation. He also worked as a reservoir engineer for Apache Corporation, and he graduated from Texas A&M University with a bachelor's in petroleum engineering in 2008. Kyle Hanna is a senior reservoir engineer, or is a reservoir engineering specialist at Unconventional Subsurface Integration, or TechUSI. He also worked as a floor hand at Latshaw Drilling full-time from June 2021. He graduated with a Bachelor of Science and Petroleum Engineering from Texas A&M University. Now I'm going to talk a little bit about Tui Nguyen. He's a software developer at Unconventional Subsurface Integration, or better known as TechUSI. He also worked as a software engineering intern at Sensei Tech and a data management at Hong Kong Food Market. He graduated with a bachelor's degree in computer science at University of Houston and also got his University of Economics degree and a bachelor's degree in economics. Welcome to the podcast, all of you.
Thank you, Yoshi.
Thanks, Yoshi. It's a pleasure to be here.
Thank you, Yoshi.
Well, I have to admit, I always have a pleasure doing these podcasts, no matter where I'm at. And before this podcast recording, I was telling you guys that I'm stuck in Denver and just doing my traditional MBA program. And it just comes with the territory being stuck in a place, but I always get a kick out of doing these podcasts. So I'm really happy to have all of you on the podcast, and doing this paper together was really fun to do, and doing the work. And I really was excited when I read the paper, was doing the paper and presenting the paper, to the point where I think people need to have a better understanding about the paper. And I wanted to have all of you guys on this podcast, so it's great.
Absolutely.
Well, to orient our viewers and listeners, I was wondering if you guys can briefly describe the paper and the methodology of the paper.
Yes, absolutely, Yoshi. So the paper presented infill spacing optimization result, applying our new methodology and application for Midland and Delaware basins. We have since expanded to several other unconventional basins in the U.S. So that's the Eagle Ford, Powder River, DJ, and Williston Basin. We have taken pre-run reservoir simulation in fully gridded models using parameters that are representative of a specific basin, and using those simulated type curves, train and tune the neural network models. Reservoir engineer can then apply these deep learning models to define their own set of development inputs and arrive to a physics-based answer for well density optimization.
Excellent. Duke, I wanted to add something that just came into my mind. When we did the technical special podcast, it was really popular.
Oh,
so
great.
I was just letting you know that a lot of people were excited to hear about your story and hear about this technology too. So I wanted to add on to that.
Appreciate it, Yoshi.
Yeah, I think this was, I think the paper just speaks volumes on some of the stuff that you guys have done. I wanted to get to the weeds of the paper a little bit. And Kyle, I think you can best explain this. If you can explain this for our viewers and listeners, how detailed is the base numerical model set up before we forecast the millions of type curves?
It's a really good question, Yoshi. So we've basically parameterized everything possible in a modern reservoir simulation model. So all the petrophysical characteristics, water saturation, permeability, porosity, producing formation thickness, bubble point, reservoir pressure, compaction tables, relative permeability curves, and KV/KH ratio. So then we also go in and parameterize the completion and production parameters, like the drawdown profile, including startup and minimum bottom hole pressure, the fracture half length, height, permeability, and water saturation within the fracture are then also parameterized. So without inputting actual subsurface mapping, it's about as detailed as we can make it.
Excellent. I was also reading more about the paper and doing the work with you guys. And one thing our viewers and listeners may not have a familiarity with is just the neural networks model. And Tui, you can go more into detail of this, but the sequential model or the Keras sequential model was used. And the paper goes more into detail of what kind of coding language was used, what kind of model was used, like ReLU was also used, and for optimization. So I was wondering specifically for Keras sequential model, why was that selected?
Yeah, because Keras is a powerful and easy to use, also free open source Python library for developing and evaluating deep learning models. So our problem is that we predict the cumulative type curve of oil and gas and water for 30 years time series. So Keras model along with Keras tuner library is the perfect choice for this problem.
Awesome. Thanks for that. And do you want to, so it's a free open source Python logic. Okay, so you actually talked about that. I was just going to ask if you can go more into detail what exactly that was, but you already talked about that. Now I want to talk to you, Kyle, because you talked about the base numerical simulation model. So what kind of ranges of compaction tables are used to take into account geomechanical properties, especially in the Permian Basin?
Another really good question. So we actually applied genetic algorithms to derive our compaction tables from available production and pressure data. So then depending on the calculated slopes for the specific area of interest, so in this case, the Permian Basin, different porosity and permeability multipliers will then be applied at various reservoir pressures. So we currently stop over here and haven't really gone deeper into the geomechanics. And this is in an effort to prevent the neural networks model from overfitting the data. Detailed geomechanical properties will at some point be incorporated in future neural network models.
Okay, that's something exciting to know for geomechanics and how to balance that overfitting. I'll probably ask you later on in the future of how do you know when you've overfitted, or how do you, like, what's the limit of overfitting or not?
Yeah.
You think you can answer that right now?
I think Tui, you can try, Tui.
Okay, what was your question?
Oh, the question was, how do you know you've overfitted the model?
Oh, when we train in the model, so we have to we have a function called early stopping. That is a most thing important to stop the overfitting. So whenever the hold on, let me.
That's okay. We can go on and talk about other things, but there is a limit. There is a functionality to know when you've overfitted the model.
Yeah, well, yeah, there is a limit, and also, we are feeding the model with so many parameters at the moment, and that if we actually incorporate more geomechanics like stress and things like that, it's going to kind of having kind of overwhelming set of parameters. So right now we kind of pauses at the compaction table, but in the future, why we already kind of fine tune all of these models for all the basins. Then we will come back and revisit this geomechanics problem.
Cool. Thank you for that.
Mhm.
Tui, I wanted to talk to you about the Python script because I don't know if our viewers and listeners know that there's a Python script that gets integrated into the neural network in order for us to come up with the best fit forecast simulations. So I wanted to know, how does a Python script get integrated to run the neural network?
That's a great question. So our model have to handle a huge amount of prediction as we create millions of curves. So with Python data frame, we manage to process millions of curves or return them to the SBF application as fast as possible. The entire framework of processing data, training data, and applying data were built on Python script.
Okay. Okay. Well, I was thinking about this paper and I was thinking about the workflow that we've worked on. And one thing I've noticed is that it is meant to address a problem. It's meant to address some of the limitations that we've seen in the industry. So Kyle, I was wondering if you can talk about or go into detail some of the limitations of our current industry forecasting methods.
Yeah, sure thing, Yoshi. So I'll start with what's arguably the most commonly used solution, and that's decline curve analysis. More commonly today, we've actually seen a machine learning applied to decline curve, which is everyone just calls data science. So a lot of the assumptions around the derivation of the ARPS equation, which is the foundation of DCA, limit its applicability in unconventional resources. So the question to us is this really sustainable long term? The industry as a whole suffers from noisy and incomplete data. So if you go and look at any sort of publicly available production data, you're going to find that a lot of it is just allocated data and in some cases, there may be early production profiles or no production at all, which creates input and output uncertainty in our well predictions. Moving on, we also see the statistical scaling of lateral length and arbitrary risk factors that are assigned to these decline curves. So taking a decline curve analog from one area or from one lease and then applying it to a new development area. And then that raises the next question of, if we're using these analog wells from another area, we may have early production data that may not yet show interference, which will then yield significantly overstated long-term forecasts. And then more specifically, especially in the Permian Basin, we then see that we have limited data samples. So with the advent of stacking, as in the Permian Basin, you have multiple producing formations and we want to maximize our profitability. So we stack wells in there. Well, these are new areas with limited data, and just our empirical methods just simply lack the critical amount of data and cannot be predictive in these new areas. So then I'll move on to rate transient analysis. And this is still based on single well models that cannot handle well-to-well interference. So initialization of infill well hydraulic fractures during the primary production periods are still very, very tricky. So then that takes us on to our physics-based modeling, so numerical simulation, geomechanics, etc. And this is the only method which is really capable of calculating fracture interference properly. But the major downside is that it is very time-consuming and very resource-intensive to build a descriptive model, which is then going to tend to overfit the data. We want to get the best match possible. But at the same time, then that model cannot be taken to a new area and be predictive due to the nature of it overfitting the data.
Okay, thanks for that clarification. I wanted to pivot a little bit back to neural networks. So I was just curious to know, Duke, what are some features of significance in the neural network model? And you're on mute.
Yeah, Yoshi. So yeah, this is this is really a brand new thing for us. There's a lot of things that we can talk about, but I probably just highlight two main features of the neural network model that we're building. First, it generates physics-based type curves in seconds compared to numerical simulator, which takes days or months to do the same job. And secondly, it's calculate dependent variable, so that's well spacing, infill timing, and FDI factors, which are the SRV overlap percentages from well to well, while generating type curve, which really is the first time our industry can do something like this.
Awesome. I was also wondering, now I wanted to get back to the weeds of the paper because that's what I do. And you have so we have a figure in the paper and it's a box model. And it's for SRVs for reach and overlap. I'm just wondering, there have been claims in the industry that there are contributions that come from outside of the box model. So how does the tool take into account production contributions that could be outside of the box, Kyle?
Yeah, that's another great question, Yoshi. So by using a full-scale reservoir model, the reservoir simulator actually does take into account fluid flow through porous media. We then train the neural network based on these simulation runs, both single and multi-well. And the neural network model learns that the well does produce from beyond the stimulated rock volume. And this is because we've gridded the model so that there is sufficient volume outside of the bounds of the simulated rock volume to allow the simulator to see the contribution from this non-SRV. Sorry, non-contacted SRV.
Non-contacted SRV. Okay, awesome. Yeah, I've always wondered that, and this is good that from the runs they do take into account it's beyond the stimulated rock volume. And I know there's pressure depletion that takes into account that fluid flow when we've talked about it in the workflow when we've done the work together. Now I wanted to pivot back to you, Duke, in terms of the case studies. And the case studies talk about, one of the case studies talk about top-down sequencing in the paper. And there was a 2 million MBO difference between top-down versus bottom-up. But one thing I've noticed in the industry is that not everyone really has adopted that yet. So I'm wondering, why do you think the industry hasn't adopted the sequencing yet?
Yes, Yoshi. Well, I believe both sequencing have been applied in our industry is a case-by-case basis, but the reasoning for one versus the other have been, mostly based on drilling rights and land-related issues, and we didn't really have the capability to evaluate the incremental EURs for oil and gas field on a case-by-case basis. So we do have that ability now with the neural network modeling from a physics-based model, quantifying these depletion effects over time across multiple benches.
Okay. So it is a case-by-case basis. And I guess with more communication with operators, for example, we'll be able to get a better understanding of whether that top-down or bottom-up sequencing is feasible.
Absolutely.
Awesome. Well, I've peppered you all with a bunch of questions, and I know I've also thrown some curveballs at you guys because I think this paper needs to get to as many hands as possible, and people need to understand the workflow. And this is a reverse engineering of numerical simulation, and I've been very excited about the workflow. There's one question that I can't let any of you get away with. So this is a popcorn question. You guys can, any of you can take this as much as you want, but what are some implications of this paper that we have never seen before in this industry?
I'll go ahead and take that one. Truly, the ability to integrate physics-based and data-driven models into one solution is really the new concept here. So what does this mean? This means that we can now achieve the accuracy of a physics-based modeling solution with the speed of data analytics. And we truly believe that this is the direction that our industry is going to head.
Awesome.
I probably going to add one more thing. So with a click of a button, you actually can generate any type curve that you want for any development scenarios. That's really the bottom line.
No, and that's what's exciting. I've been telling this to do, but this is a video game.
Yeah.
This is
Yeah.
literally a video game for me, like trying to find the match, trying to figure out what is like what's going to be the predictive capability of the developments it's very exciting. And I just want to iterate that I had a lot of fun with the paper and had a lot of fun with the workflows. So I want this to get into as many hands as possible, and I hope you guys have a lot of feedback on the paper too. So this podcast is meant for that. Well, thank you so much for letting me pepper you all with questions, guys.
Yes, absolutely. Thanks for having us.
Thank you, Yoshi. Really appreciate the opportunity.
Of course.
Thank you, Yoshi.
Of course. Well, folks, that's a wrap for ERTech 372-3394. Please be sure to check out the paper. Reach out to me if you have any papers or if you'd like for me to interview anyone else on the podcast and let me pepper them with questions. I'm Yogeshri Pradhan, and we're signing off.